Hello and welcome to Conceptual Physics at Delaware Tech, Chapter 14, Gases. Well, like the previous two units on solids and liquids, we're going to focus on the physical properties and physical behavior of gases. So first we'll talk about the atmosphere and some properties of our Earth's atmosphere. We'll talk about atmospheric pressure and how it's measured and what it is. We'll talk about one of the ways we measure it, and that's with a device called the barometer. Then we'll talk about Boyle's law. Boyle's law is a relationship between the pressure on a gas and its volume, and it's an inverse relationship. Then we'll talk about buoyancy of air. We've already spent a lot of time talking about buoyancy in liquids, especially water. The rules are exactly the same, it's just in air instead of water. Then we'll cover Bernoulli's principle, a very, very misunderstood principle. We'll go over where it comes from, but I'll make some mention about some examples that are given to you. And then we'll talk about plasma. Plasma is the so-called fourth state of matter after solids, liquids, and gases. There are actually many states of matter that most people are unaware of, but the typical fourth state after liquid, solid, and gases is plasma. Okay, so the atmosphere, Earth's atmosphere. It's essentially an ocean of air that surrounds the Earth. And because it has weight, because it is matter, all matter has mass, and mass exposed to gravity, like Earth's gravity, has weight. So weight or force per area is pressure. So the atmosphere exerts a pressure on the Earth and everything on the Earth. And one of the first demonstrations that there even is an atmosphere happened in the mid-1600s in the town of Magdeburg in Germany. And this was done by a scientist slash politician named Otto von Guericke. And what he did was he took two halves of a sphere, two metal halves of a sphere that could seal together. He sealed them together, and then he pumped out as much air as he possibly could. And these things had rings on either end, and he attached them to teams of horses on either side of them. And he did this demonstration for the Holy Church from Rome. He also did the demonstration for the King of Prussia, and they were so impressed. The King of Prussia gave him a pension for life after seeing this demonstration that he could stop teams of horses from pulling. They were unable to pull it apart. Now, what this demonstrates is the fact that the atmosphere around this metal sphere was pressing, the air was pressing on all directions around the sphere, keeping the sphere intact. Remember, it's two pieces that could easily fall apart, but it was just a vacuum on the inside. And it's a misconception that the vacuum is sucking the pieces together. Vacuums don't suck. What they do is they remove air or whatever other matter is in there and allow the atmospheric pressure to push. So the atmospheric pressure was pushing this thing tight, even though there was nothing, because there was nothing inside of it. The pressure on the inside couldn't equalize the pressure on the outside. So the pushing in is much greater than what little pushing out there was from inside, and it kept the spheres together. And this demonstrated that there must be something in the air, something in the atmosphere surrounding people, even though people couldn't see the air surrounding them. So atmospheric pressure is due to the weight of the air. Okay, if you made a column of air right up to the top of the atmosphere, and there is no real definite top, it just gets thinner and thinner and thinner. So if you ask somebody how high at what altitude do we stop having atmosphere, there is no good answer. You'll hear people say, oh, it's a few kilometers. You'll hear other people say it's 100 kilometers. You'll hear other people say much, much further. It all depends on what you call atmosphere, how little gas molecules are still considered atmosphere. But this atmosphere that is surrounding the Earth is there because it has weight. It's settled down by the the gravitational pull of Earth, pulling matter down. But at the same time, you have random movement as well as definite movement from kinetic energy in these molecules of air, mostly nitrogen and oxygen, but some other gases. And they're moving around, and if there was no gravity, that movement would eventually scatter the gas away from the planet Earth, and we would have no atmosphere at all. But gravity is what keeps it pulled down, and also magnetic field is what keeps it stabilized, but that's a whole other discussion. So gas, like any gas, including air, like any liquid, are considered fluids. Fluid is anything that flows, and that includes both liquids and gases. So the atmosphere, as I already mentioned, is not uniform. It'll vary in altitude. It gets thinner and thinner as we go to higher altitude. There is less gravitational pull. There is just the kinetic energy of moving the molecules around. There are winds that might be blowing particles around, but you also have the varied geography of the Earth as you go around the planet. There are mountains, and there are plains, there are oceans, there are all kinds of landforms and water forms surrounding the Earth, and that will make the atmosphere surrounding them be fairly uneven. It's mostly even, but there are significant variations from one place to another, and this is essentially why we have weather and climate. So measurements are used to predict weather conditions. I think we all know that. We watch the weather on TV or on your computer or on your phone, and people are able to predict the weather mostly accurately. It's a prediction, so it's never perfect. But what you find is that low atmospheric pressure tends to be associated with bad weather. In fact, when you look at barometers, a lot of times barometers might have a dial on it, and in the middle it'll say changing weather. And on the right side in high pressure, it'll say it's getting nicer, it's fair weather, it's dry. But if you look on the left, it'll start saying rainy, cloudy, or stormy, because bad weather tends to happen when the atmospheric pressure is low. Now, when I say low, I mean a little bit lower, or when I say high pressure in the atmosphere, it's a little bit higher. It's not a gigantic range, but it's enough to be significant in terms of its effects on weather. Now, the amount of weight of air might very well surprise you. It surprised me when I started doing calculations on it. The pressure is exerted against everything on Earth. You feel that the pressure is due to the weight of the air on top. And if you made a square on the ground that was 1 meter by 1 meter, and you asked how much weight is sitting on top of that square, well, it turns out the amount of weight sitting on that square is about 101,000 newtons of weight. That works out to, divided by 10, that's the number of kilograms, about 10,000 kilograms, or about 22,000 pounds of air sit on every box that's 1 meter by 1 meter. That's an enormous amount of air. When you measure pressure, pressure is in units of force per area. We've talked about this before. Pressure is defined as force per area. In this case, the force is weight per area. So our weight units are newtons or pounds if we're in the imperial, and our area units are meters squared or feet squared or inches squared if we're in the imperial system. So it's 100,000 newtons per square meter. That's what's sitting on top of a square meter of area on the ground. 100,000 newtons of weight, about 10,000 kilograms or 22,000 pounds of air sit on it. That's a gigantic amount of weight sitting on it. And you might wonder, well, how are we not crushed by all that weight? Because even if you look at 1 foot, a 1 foot square, that works out to a little over a ton of air sitting on top of you at any one time. And the reason you're not crushed is your atmospheric pressure in your body, as well as the liquid pressure in your body, balances it perfectly. So we're not crushed, and we've been living with it since birth, so we don't even notice it. So our internal pressure is exactly equal to the external atmospheric pressure, and we don't feel this force per area on our body because we have the same force per area on the inside of our body. All right, so we have this enormous amount of force. The units we use, newtons per meter squared, were named after Blaise Pascal, so we call them a Pascal. So it's roughly 100,000 pascals of pressure is what the typical atmosphere is. Another way to state that would be 100 kilopascals, kilo meaning 1,000. So when somebody says 100 kilopascals or kilopascals, they mean 100 100,000 pascals, or 100,000. The actual number that scientists use is 101,325. We're not going to get to that detail. 100,000 is close enough. Okay. So it turns out if you took the weight of any column of air, so if you made a meter squared and you said, what's the weight? Well, it's 101,000 newtons of weight on top of that, 22,000 pounds roughly, right? Well, if you said, okay, well, how high would a column of water have to be to match the weight of that air? So if you have a column of air that goes all the way up to the top of the atmosphere and you said, what's that weigh? And then you said, okay, let's make another column made of water. How high do we have to go in the water to get the same weight? Well, the height we have to go to is 10.3 meters, or about 34 feet. So 34 foot tall tower of water, no matter how big you make it, is the same weight as the same size tower, the same width tower of air that goes all the way up to the top of our atmosphere. That's a big difference, but that's because water is much denser than air. Enough so you can squeeze it down to 34 feet, 10.3 meters. Well, the problem with that is this. Since the pressure of our air at the bottom of our column, remember when we were talking about water, the pressure is due to the depth. Well, it's the same thing with air. We're at the bottom of the tower of air. And if you ask yourself, what's the pressure here? It would be the same as if you were at the bottom of a tower of water that was 34 feet deep or 10.3 meters deep. It's the same pressure at the bottom. That amount of water will exert exactly the same amount of pressure on you or whatever object as the entire atmosphere exerts on you. And what that means is we are limited when we make pumps. So a lot of people have a misconception about how pumps and vacuums work. I already mentioned this with the concept of vacuum with the experiment I showed in the first slide. But think about it this way: when you're using a pump, it's as if you had a syringe that was empty, and you're putting the syringe in water, and you're pulling up with the syringe. You're creating a vacuum, yes, because there's no air in there when you're pulling up. Well, what's actually pulling the water into your syringe is not the vacuum; it's the atmospheric pressure on the other water pushing the water down and into the syringe. So it's the weight of the air, that giant column of air that goes all the way up to the top of the atmosphere, pushing down on water, pushes that water in. And that's what allows us to get what we think of as suction. It's actually a pushing by the atmosphere, not the sucking from the vacuum. And pumps work exactly the same way. When you pump, you're removing the air from the tubing that goes down, and the atmosphere surrounding the water at the bottom of your well is pushing down the water back into the pipe so it goes up to the top of the well. Well, the problem with that is, remember, the entire height of the atmosphere has the same weight as 10.3 meters or 34 feet of water, whatever pipe we make, okay? It'll be the equivalent of 10.3 meters of water, 34 feet. Well, what that means is the atmosphere can never push more than 10.3 meters of water or 34 feet of water. It can never push that much. No matter how hard you pump, no matter how good a vacuum you get, the atmosphere doesn't have enough weight to be more than the weight of 10.3 meters high of water, 34 feet of water. And because of that, no matter how hard you pump, no matter how hard you suck, you will never be able to draw water up a tube higher than 34 feet. It is absolutely impossible as long as you're on planet Earth. Now, mechanical pumps, these are pumps that have a different mechanism of action. They actually have a mechanism of pumping that doesn't rely on the atmospheric pressure pushing them down, and they don't have this 10.3 meter or 34 foot limit. So you might be thinking, well, I know of pumps that do more. Yeah, those are mechanical pumps that have a whole different mechanism of pumping action. All right, so what's the maximum height that anyone can drink water through a straw at sea level? You probably already know the answer. A, 10.3 meters, B, about 76 meters or 760 millimeters, and we'll talk about why that number is important in a few minutes. There is no limit, none of the above. Well, as we've already stated, it's 10.3 meters. No matter how hard how strong your lungs are, whatever device you have, no matter how good a pump you have, the best you can do is create a perfect vacuum. That's the best you can do. Unfortunately, once you create that vacuum, the only force available to push liquid up into the straw is the atmosphere pushing on the rest of your glass of water or whatever you're sipping from. And the weight of that water is never going to be more than the weight of a height of water 10.3 meters high. It will never, it's exactly the same, so it can never push more than that. There's just not enough weight of air. If we were in a place where the atmospheric pressure was higher, there'd be more weight pushing down and could push the water up a little bit higher. If you were on another planet that had a super dense atmosphere, you could get the water to go up even higher still. If you were on a planet that had no atmosphere, think about that. You wouldn't be able to suck liquid up a straw at all if you were in that environment. So remember, when you're sucking, it's not the vacuum that's pulling the water up, it's the surrounding air that's pushing pushing the water down and then up into the straw or whatever piping you're doing. The atmospheric pressure is only strong enough to push water up to a height of 10.3 meters, no matter how good your vacuum is. Doesn't matter. So the barometer was a device to measure the atmospheric pressure, and we've already talked about how the whole column of air has the same weight as a 10.3 meter column of water, because water is so much more dense than air. You can shrink that column down to 10.3 meters if it's water. Well, it turns out if you instead of using water, you use mercury. The symbol for mercury is Hg in this diagram. Hg, that's the chemical symbol for mercury. It comes from an ancient Latin word hygrargentum, which essentially means liquid silver. That's what they thought mercury was. Something like that. Quicksilver was the old name for mercury. So mercury is even denser than water. In fact, it's 13.5 times denser than water. So what that means is instead of 10.3 meters of water that the atmospheric pressure can push up, you can only push up 0.76 meters of mercury because it's so much denser. So that's 1/13.5 fraction of that 10 point. If you take 10.3 meters and divide it by the density of mercury, 13.5 grams per mil, you can shrink your column down to less than a meter, 0.76 meters, 760 millimeters, or 76 centimeters, depending on which unit you want to use. All right, and that's what Evangelista Torricelli did in the 1600s. Torricelli wanted to make a barometer, something to measure the atmospheric pressure, and he was aware that the pressure of the air was pushing down. So what he did was he took a tube that was sealed on one end, sealed on the bottom, filled it with mercury, filled it right up to the top with mercury, and then he essentially put his finger on the top, inverted it, so the sealed part is on the top and the hole in the bottom that he's holding, and then he put it in a pan filled with mercury, and then he let it sit. And because the weight of the mercury is so heavy, it's so dense, it settled down, but it didn't settle all the way down. The reason it settled down is because gravity was pulling the mercury back into the pan that it was sitting in. But the reason why it didn't pull all of it down is the atmospheric pressure on the mercury in the pan, these outer two red arrows pointing down, provided the balancing force, the force of the atmosphere, the weight of the atmosphere, balanced the weight of the mercury so that eventually the mercury found a happy medium. Now, of course, in doing that, it created a vacuum at the top, but we're not going to worry about the vacuum at the top. And that height, he measured the height in his container of glass, his tall container of glass, and he saw that it was 760 meters high on most days, on the average day. And to this day, we refer to one atmospheric pressure as, quote unquote, 760 millimeters of mercury. You may have heard that. You may have heard weather people say, oh, it's this many inches of mercury on the barometer. Well, they just changed it into inches. So this would work out to just under 30 inches, 29.9 inches of mercury. And you'll hear weather people say, oh, the pressure out today is high pressure. It's 31 inches on the mercury, or of the mercury. They're talking about the barometer based on this original barometer from the 1600s. So it's the atmospheric pressure balancing the weight of the mercury. So that's how he made this thing. And the millimeter of mercury unit, which is used especially by chemists to measure atmospheric pressure, is also called the torr, named after Evangelista Torricelli. So it was named in his honor. So millimeter of mercury and torr are exactly the same unit. They both equal 700, well, and 1 atmosphere pressure is defined as 760 millimeters of mercury, or 760 torr. And 1 atmosphere pressure is also that unit I told you about before, 101,000 pascals, or newtons per meter squared. And we're going to stick to the newtons per meter squared. We're going to use the unit from the SI system that most physicists favor. So here it is, 760 millimeters of mercury, or 760 torr, is about 101,000 kilopascals. It's actually 101,325. I'm sorry, 101,000 pascals, or 101 kilopascals, but it's actually 101.325 kilopascals. Don't worry about the fraction. All right, so why don't barometers use water instead of mercury? A, water cannot be used because it doesn't exert pressure. B, water cannot be used because it sticks to the glass. C, water can be used, but the barometer may be too tall. D, none of the above. Well, I gave you a few hints. Remember, a column of mercury, 760 millimeters high, has the same weight as the same width column of water, 10.3 meters high. So the answer is, you would just have to have a really, really tall barometer. You absolutely could make it with water, but because mercury is 13.5 times denser, water, you'd be able to push a column of water much higher in your barometer, 13.5 times higher than that 760 millimeters. Well, that works out to the 10.3 meters that we talked about, or the 34 feet. So your barometer would have to be taller than that. And most people don't want to have a 40-foot barometer sitting in their house. 1 meter is long enough. When it's mercury, you have to have a little extra space above that 760 millimeters. So a meter-long barometer is already pretty big. An 11 or 12 meter barometer is going to be really unwieldy. Now, there are other kinds of barometers that don't use mercury at all, and that you could actually fit in a very small space. And one type of barometer is called the aneroid barometer. It's aneroid. It's actually a word that means without water, because if you were to make that water barometer, it would be 34 feet. So barometer, the word barometer means measuring the weight. Baro comes from a Greek word. Baros means weight. You may have heard the element barium. It's a very heavy element. It was named for its heaviness. And meter just means measure. So barometer literally means measure the weight, in this case, the weight of the air. It's really the pressure of the air, because it's the weight divided by area, but it's the pressure we're measuring. And the way this barometer works is completely different from the ones we just talked about with mercury, or potentially with water. This one has a little box at the bottom, a metal box that's flexible. It can squeeze tighter or expand a little bit, and it's flexible. And some of the air has been removed from the box, so it's very sensitive to atmospheric pressure on the outside of the box. So if the atmosphere is much higher than what's in the box, it'll start squeezing the box tighter. And if it's a low atmospheric pressure day, the box will get a little bigger. And there's a little device that's attached to the top of the box that moves, that eventually is connected to a needle. So what happens is, when the box lid bends in or out, that is due to changes in pressure. And the motion of the lid is connected to the indicator arrow. And what you'll see is that in low pressure days, the arrow will go to the left, and high pressure days, it'll go to the right. And you'll notice the units in this, the numbers on this range from 27, 28, 29, 30, 31, all the way up to 32, which is not written on this, but it's in a circle here. Well, that's the equivalent inches of mercury. Instead of millimeters of mercury, it's in inches. So remember, the average day, 760 millimeters, is equal to 29.9 inches of on the mercury scale, which is what they're showing on the scale. So this day shows that it's just a little bit below the normal, the average pressure. It reads 29.6, so that's a slightly low pressure day. And you'll notice on the left side of this it says storms, and on the right side of this it says fair and very dry, because low pressure days are associated with bad weather and high pressure days are associated with nice clear weather. This same type of device can also be used to detect elevation, and that is because the atmosphere gets thinner at higher elevations in a very regular pattern. There's actually a formula for calculating it. So if you take a device and you move it to higher altitudes, the pressure will go down, and by measuring the pressure, you can convert that information into altitude. So altimeters, these devices to measure altitude, are frequently based on the atmospheric pressure that it experiences as something goes up higher, like an airplane or a balloon or whatever you're measuring, or if you're just on the top of a mountain and you want to know the elevation. They're not incredibly accurate for elevation, but close enough for anybody flying. All right, so Boyle's law. Let's talk about Boyle's law. This is named after Robert Boyle, but the fact is two other guys, especially Henry Power and his friend Henry Power and Richard Townley, they actually did these experiments first, and Boyle reported his experiments and even mentioned the paper by Powers and Townley, but he forgot to mention Powers' name, who was the real person who did these experiments. But because Boyle was so famous already and pretty rich, they named this law after him, and we still call it Boyle's law. But Boyle's law is something that was worked out in the mid-1600s by all three of these people, and it's a relationship between the pressure of a gas and the volume of a gas. And what they all found was that as the pressure increases, the volume decreases. As the pressure decreases, the volume increases. And so you can either change the pressure or you can change the volume, and the other one will do the exact opposite. They are inversely proportional. So P is proportional to 1 over V. Another way to say that would be to multiply both sides by V, and it says that P times V is proportional to 1, which is essentially saying P times V is actually equal to some constant we haven't written in here. So P times V is constant. That means if you have a gas and all you're changing are volumes and pressures, in other words, you're not touching the temperature, that'll mess things up. And you're not adding or taking away gas, that'll mess things up. So, but if all you're doing is mucking with the pressure and the volume, if one goes up, the other goes down. And if you multiply the two together, you will get the same number as even if you change the pressure and have a new volume. Whenever you multiply them together, their product will be the same value. And as a result, you can do an experiment like the one shown in the bottom here, where you have this piston. In the left, you have a piston where the volume is bigger and the pressure is lower. You look at the gauge, you can see the pressure is on the low side, and that is because the air has much more, or air or whatever gas is in there, has much more room to move around. And because of that, it has more area, more surface area on the walls of the container to bounce off of. Remember, what is pressure? Pressure is a force, and the force is from the molecules bouncing against the wall, force divided by the area. Well, in a big container, you have a lot of area. So it's force divided by a big area, so you have a low pressure. Whereas when you squeeze it tighter, your volume is going down. Because you have less volume, you have less surface area for the molecules to bounce against, and they're still producing the same force. They're still moving the same speed. They're going to hit the walls more often because there are less walls. And therefore, the pressure will go up. You have the same force divided by a much smaller area, so your pressure goes up. So what this means is volume goes down to the second piston, the pressure goes up, and you can see the molecules are hitting the walls more frequently. And that's what Boyle's law amounts to. And this is really a consequence of pressure being equal to the force, which doesn't seem to be changing, divided by the area, which is definitely changing in a smaller volume. So a typical example would be if you half the volume, you will double the pressure. If you tripled the volume, you will cut the pressure down into thirds. If you multiply the volume by 10, you will divide the pressure by 10. If you shrunk the volume to 1/10, you will increase the pressure tenfold. It's always the opposite. Whatever you do to one, the opposite happens to the other. So pressure and volume are inversely proportional to one another, okay? And the other way to write that would be pressure times volume in one situation is equal to pressure times volume of the other situation after you've changed either the pressure or changed the volume. You can change either one. As long as you're not changing how much gas is in there, the mass in there, and you're not changing the temperature, this relationship holds very well. So a large pressure will be associated with a small volume, and a small pressure will be associated with a large volume. It just has more room to bump around, so the pressure goes down. So a piston is in an airtight pump. Okay, so it's a piston that can move up and down and change its volume. It's sealed, so nothing's getting in or out. And so you have a pump that is withdrawn. In other words, you're pulling it up. The piston's pulling up. So the volume of the chamber is increased threefold. What's the change in the pressure? Well, if you increase the volume threefold, you have more room for the gas to bounce around, so the pressure will go down threefold. In other words, the pressure will become 1/3 of the original value. Inversely proportional, right? The volume's increased 3 times, the pressure will decrease 3 times, which it means it's 1/3 of its original. That's because the gas particles have 3 times more room to bounce around in, and they have more walls to hit, so the pressure decreases threefold. All right, so let's talk about buoyancy in air, the buoyant force. Now, we've already talked about this in water a lot. The rules are exactly the same. Archimedes' principle applies to all fluids, not just water and other liquids, but air and other gases. So an object surrounded by air, and this includes you standing in the air, is lifted up, we call it buoyed, by a force equal to the weight of air that object displaces. In other words, we look at the volume of the object, it's all surrounded by air, the volume of air that would have been there, and we ask, what would that air weigh? That is equal to our buoyant force. So first you measure the volume of the object, because in this case, we're not talking about the object floating to the top, and we don't have to worry about the water line or the air line. There is no air line. So the object is always surrounded by air. Okay, so it's always the whole volume of the object, and the whole volume, its whole volume in terms of air and that weight of air that we're concerned with. All right, so we measure the volume of the object, we determine the volume of the air, that would be the volume of the air displaced, and then we ask ourselves how much weight is that? That weight of the air that's displaced is the buoyant force. So if there's more pressure, and the buoyant force here is for the exact same reason as you see it in water. The pressure of the air on your feet is a little higher than the pressure of the air on your head, or the pressure of the air on any object is higher at the bottom than it is at the top, and that's because there's more air pushing on the bottom than there is on the top. It's a small difference, but it is a real difference. So the rules for lighter than air objects are very similar to the rules for lighter than water floating objects in liquids. When the weight of the air, in other words, the buoyant force, is greater than the weight of the object, because it's always two conflicting forces, the buoyant force pushing up and the weight of the object pushing down. If the buoyant force of the air is greater than the weight of the object will float up. It'll accelerate upwards. If it's exactly equal, the object will just kind of hover there in space, in the air, not in space, in the air. It'll be balanced. That way the forces are identical, so there's no acceleration up, there's no acceleration down. There might be constant movement up or constant movement down, but there's no acceleration. And that is when the buoyant force is exactly equal to the weight force, the force due to gravity. All right? There's what we call it hovering or suspended in air. That is a situation where the net forces are zero. So it's neither rising nor falling in the air. And then the third situation is when the weight of the air, in other words, the buoyant force, the weight of the air that's displaced by the object is less than the weight of the object. So it's not supported by the air. Well, that means if the object's already on the ground, it's not going anywhere. It's not lifting up. And if the object's already in the air and this happens, it's going to start to sink. It's going to start to fall and accelerate downwards because the force of gravity is greater than the force of the buoyancy of the air pushing up. So gas-filled balloons, these include dirigibles, blimps, and zeppelins. And here's a picture of a typical blimp. And these are filled with gas that makes them lighter than the atmospheric air in terms of density, lower density. So they have a buoyant force greater than their weight. The amount of air that they displace, air that would have been where the blimp is heavier than the blimp. And therefore they rise up. And if they balance the weight of the blimp to the amount of air they are displacing, then they'll just hover there, and they can move up and down in a constant speed, or they can move across, but they're not going to be accelerating up or accelerating down. And the best gas to do this with is hydrogen. Hydrogen is the lightest gas on the periodic table, and it has the lowest density of any gas that any normal gas that we can create. The problem is hydrogen gas is crazy flammable. If it's exposed to oxygen and a little spark happens, it will ignite, and hydrogen gas plus oxygen gas produce water. That's water vapor. It's not going to put out that fire. That fire is huge. It's very energetic, and unfortunately, this is what happened in 1937 in Lakehurst, New Jersey. It's a very famous event. I'm sure you've heard, a lot of you have heard of it. It's called the Hindenburg. The Hindenburg was a German Zeppelin, a German blimp that was flying in from Germany to New Jersey in 1937. And to this day, they're still not exactly sure what ignited the fire. It might have even been sabotaged. It probably wasn't. It was probably some faulty device or something hit or a spark hit. But the hydrogen ignited and the whole thing went up in flames, and about a little more than a third of the passengers and a third of the crew perished in this horrible incident. There's actually recordings of the reporter who witnessed it. To this day, they're very heart-wrenching to listen to. But this is why we don't use hydrogen gas anymore. It's just far too dangerous for most types of balloons. Small balloons you might use it for where that's not a problem. So the next best thing is helium gas. It's number 2 on the periodic table, and it's still a very light gas. We use it for helium balloons, but the problem is helium is not an inexhaustible a resource that we have. There's not a lot of helium on Earth. There's a ton in the sun, and there are a ton in most stars, but there's very little on Earth. Most of the helium we find is actually above natural gas deposits or other fossil fuel deposits deep underground, and it's pumped out. So we sell helium for everyday balloons for kids' parties, but the fact is, Earth is running out of helium. It's something we absolutely need for research and technology, for superconductors. So it's unbelievable to me as a scientist that we just sell this for kids' toys. Yeah, they're fun to play with, but we need that helium desperately, and when we run out, we're going to be in big trouble. But the other option for balloons is just using hot air, and you've seen these sport balloons. People have balloon festivals, and they have some kind of flaming device, and it will just heat up the air. Well, hot air has a lower density than cool air around it, and when it has a lower density, it will float up. So as a balloon rises, however, at higher altitudes, there's just less air. Well, if you have less air, there's less density, there's less air pressure up there, and eventually the amount of buoyant force up top, you'll be displacing less weight of air when you're floating high than when you're floating low for the same size object. And therefore, the buoyant force is not going to be as great. So what happens is balloons will rise until they reach a level where their weight balances this decreasing buoyant force up at a high altitude, and then they'll just hover at that altitude until something else happens to the balloon. So at higher altitudes, there's less air density. So the same size balloon will displace the same amount of volume of air, but it'll be less weight of air. And remember, buoyant force is how much weight of air is being displaced. So it's going to be less at high altitudes. So a gas-filled balloon will keep rising until the weight of the balloon balances the weight of its displaced air. And another way to say that is the buoyant force will equal the weight of the object, the force due to gravity. So as a balloon rises higher and higher into the atmosphere, its A, volume decreases, B, density increases, C, weight increases, D, none of the above. Let's take these one at a time. We're floating up in a balloon. It's going up higher, and we know there's less air up there. There's less atmospheric pressure. Well, the size of that balloon is that size because that's the size of balloon that allows the outer air pressure to be identical to the inner air pressure. When you have a balloon, remember this balloon has an an open hole in the bottom typically. These are hot air. You're floating up, and the air pressure on the inside has to be the same as the air pressure on the outside when it's stopped rising, when it's getting to a certain point. And that'll be the size of the balloon that provides the pressure on the inside that balances the pressure on the outside. But as you go up higher, there's less pressure on the outside, so the balloon will actually expand because the pressure on the inside is greater than the pressure on the outside. The balloon will get a little bit bigger, especially an elastic balloon. A flexible balloon. We already learned not to use the term elastic in this case. A flexible balloon, a stretchy balloon, will get bigger at higher altitudes because there's less pressure on the outside of the balloon squeezing it in. And therefore the balloon will get bigger. Well, if you've got the same amount of air on the same amount of mass on the inside of this balloon, and it's bigger, mass divided by a bigger volume means a lower density. So the density decreases and the volume increases. So A and B are wrong right there. And the weight of the balloon is not really changing that much. So that's not going to be a factor either. So it's none of the above because the pressure is decreasing at higher altitude. The pressure and volume are inversely proportional. At low pressure, the balloon will get bigger. The gas inside that balloon will get bigger because there's less pressure squeezing it together. That's Boyle's law. And the mass doesn't change appreciably, so the weight won't change either. Okay. So if the mass is constant, the volume is larger, and the density will decrease, as we already mentioned. All right, so a dirigible, this is another name for a blimp or a zeppelin, that hovers in the air. So the key word here is hovers. A, displaces its volume of air. B, displaces its weight of air. C, both. D, neither. Well, we already know that B is absolutely a correct answer, right? That's what buoyant force means. It's hovering, so the buoyant force must equal the weight force, right? The two have to be equal for it to hover. It's not accelerating up, it's not accelerating down. So we know absolutely B is true. So the question is A true also? Well, if this was in water, the object might be floating and part of its volume be above the water that we wouldn't count. So the volume of the object wouldn't match the volume of the displaced water. But when it's in air, it's always surrounded by air. And therefore, it's always also the same volume. The volume of the object is the volume of the air. It's the whole object. It's not part of the object because the object isn't floating above, it's not floating so that part of it is in the air and part of it is above the air. That just doesn't happen. So so it's always going to be both in the case of air. In case of water, it's not necessarily true. In the case of air, it is, just because an object is always submerged, quote unquote, submerged in this ocean of air. So like a fish that never comes above the water, just stays within the water, both its volume and its weight of the fluid of the water are displaced. So dirigible's volume will displace the same volume of air, the whole volume, and that will account for that weight of air will account for the buoyant force. So we know the weight of the displaced air has to equal the weight of the dirigible. Two forces have to be equal because the buoyant force has to equal the weight force, and that is why it hovers. It neither accelerates up or accelerates down. All right, so totally new topic, and this topic is a little problematic, and it's problematic to understand, and it's problematic, even more problematic to give examples of. And I'm going to tell you right now, Bernoulli's principle is probably the most misunderstood principle in all of physics. This was discovered by Daniel Bernoulli in the mid 1700s. He was a Swiss physicist, brilliant physicist, and he came from a family of brilliant people. I heard once that there were over 100 people in his family that would qualify as geniuses. So what he found was that if there's an increase in speed in a fluid, so we're not talking about making it go faster, making it be faster, we're talking about accelerating faster, a positive acceleration. It's getting faster. So just being fast is not enough. It has to be a change in velocity of fluid, getting faster and faster. When that happens, the internal pressure, and I'll describe what I mean by internal pressure in a second, of the fluid will decrease. So what this means is when you constrict the flow of liquid through a tube, and these white spots represent bubbles of air. We'll talk about that in a second. If you have this liquid flowing through kind of in a streamlined fashion, what we call laminar flow, and we'll talk about that also. If you have this flowing through with some original velocity and a certain amount of pressure, which we'll refer to as a higher pressure, and you suddenly constrict the flow, what Bernoulli found was that the velocity of liquid increases, but that increase, as it increases, it also results in a lower internal pressure in the fluid. Now, what is internal pressure? Internal pressure is not the pressure of the whole liquid flowing out and smacking against something. It is the pressure of the liquid molecules hitting the walls, just like when we talk about gas molecules hitting the walls of a container. It's the microscopic motions of the molecules bouncing around and causing pressure that because it's a force per area of that tube. That's what we mean by internal pressure, sometimes called the microscopic pressure. All right. So why is this so? Well, in terms of conservation of energy, we can actually explain why this happens. And this is kind of counterintuitive. And so the idea here is this. Originally, when it's flowing, it has this overall macroscopic flow. It's all the molecules are flowing together. Of course, they're also bouncing around with a certain amount of energy, but they're all flowing together in this tubing. So there's this kinetic energy that's due to the individual little movements, but a lot also to the overall movement of all the molecules in the direction of the tubing, of the piping. And when you suddenly constrict the movement, it goes faster. And that's just because you have more liquid that has to go through a smaller space when you constrict the flow. So it will go faster only because there's less room for more volume, so it has to move faster to get through there. Because remember, the speed of this liquid, it's all moving together, and so you have a certain amount of volume per time, and if you've got a smaller volume of tubing, you've got to move more volume through that tube to get it all out. And this happens with a hose. In fact, you can prove this to yourself every time you take a hose and just put your finger on the tip. You're constricting the flow, and what happens? The stuff comes out much faster. That's how we make hoses spray out a lot faster in our backyard, by constricting the flow. And now the same amount of liquid that's flowing from the hose, that doesn't change. The volume per minute per second doesn't change, but you made it smaller, so it has to come out faster to get that amount. That's what's happening here. But that's not Bernoulli's principle. Bernoulli's principle says the pressure will go down, the internal pressure. So why is that? Well, the energy before that constriction happened on the left is due to the slow flow through the big tubing and the high speeds of all the little molecules bouncing around. So when you flow to the smaller tube, the whole volume is moving faster. But the law of conservation of energy says you can't have more energy on the left than you have on the right. So if you suddenly increase the macroscopic kinetic energy of the whole thing flowing, you have to decrease the microscopic kinetic energy of the individual molecules. So the individual molecules slow down inside that motion flow, even though the whole thing is flowing much faster. The little motion of the molecules is tinier, and that's represented by these little motion arrows, these little vectors of velocity shown here with the small arrows on the right and the bigger arrows on the left. And that is what explains why Bernoulli's principle works. You have lower pressure because the molecule speed has to decrease in order to give that speed to the overall flow of the liquid coming through the smaller tubing. There's another explanation for this. I don't expect you to know this. It's one that was given to me by an expert in the field. But they describe it as thinking of it kind of in the reverse direction of what causes what. They said the higher pressure region, that's the pressure, the area on the left with the big fat tubing, the higher internal pressure drives the liquid to flow through the smaller area with low pressure, because high pressure will always push into low pressure, and that's what causes the increase in speed, the increased acceleration here. So you can think of it that way if you want. It's up to you, but it's just an alternate way of thinking about the reason. Now, this only applies to what we call laminar flow. This is the smooth, steady, streamline flow. You can see these little streamlines that are drawn through this, and they're all straight and flat. The water is not tumbling over itself. It's not moving in a chaotic fashion. It's moving smoothly, either slowly or quickly through the liquid, and that's referred to as laminar flow. And the other assumption is that this is a liquid that can't be compressed. Well, most liquids can't be compressed. Not easily. I mean, you have to use millions of pounds of pressure to squeeze water into a tighter volume. So that's the only assumptions here. It's flowing in steady flow. It can be fast or slow, but steady, smooth, streamlined flow called laminar flow, and that the water isn't compressed. All right. So streamlines, these little imaginary lines going through, they represent the flow of, say, a single molecule going through here. There's no chaotic movement. It just moves through. It gets constricted, but it's a smooth flowing through of the fluid. And as I mentioned, you can speed it up by just in a hose by just putting your thumb on the end. You can see for yourself what happens. So the wider areas have higher pressure. Well, remember, Boyle's law says higher pressure means lower volume of gases. Now, I know we've been talking about liquids, and this is the volume, this is the gas chapter, but the point is this will affect the volume of the gas bubbles in the liquid, because in the big area of the tubing where the speed is slow, but the internal pressure is high, internal pressure is squeezing on the bubbles, making the bubbles smaller. But when you get to the faster moving flow that has lower internal pressure, that internal pressure is not just hitting against the walls and each other, but it's also hitting against the bubbles. And since the pressure is lower, the bubbles can expand. So the gas inside the bubble, that pressure is greater, so it allows it to expand until the pressures even out. So you have bigger bubbles on the right when you have lower internal pressure. That's just Boyle's law. Pressure goes down, so the bubble volume goes up. All right, so laminar flow is just this smooth, steady flow. So all the flow lines are parallel. They move very smoothly. You'll get them faster in the middle of the tube, a little slower on the ends, and that's partly due to the friction against the walls of whatever tubing is going through. But turbulent flow, everything goes crazy. You get winding pathways. You get these little vortices. If you look here on this drawing, you'll see these little curly cues. That's because you start making vortexes, little spirals of liquid, and it becomes very chaotic, very irregular, and very hard to predict. It's a much different type of flow, and it's called turbulent flow. You've probably heard of turbulence when people were doing river rafting. That's a very turbulent flow. When water is going over a waterfall, at first it's very laminar flow, and as it comes over the edge, it's nice, smooth laminar flow. And then all of a sudden, as it hits the ground, it hits the bottom of the water flow, it's moving around, and it's extraordinarily turbulent flow. All right, so the pressure in a stream of water is reduced as the stream speeds up. Okay, that's Bernoulli's principle. Low pressure when the speed streams up, not when it's faster, not by going fast, but by speeding up. That's a distinction we have to make. Can the stream of water from a fire hose knock a person off his or her feet? Remember, we just said that a stream from a fire hose, which is coming out super fast, it has lower internal pressure, right? Relative to before it went through the pump and was sped up. Well, we have these answers here. A, it can't, as Bernoulli's principle illustrates. B, it can, as consistent with Bernoulli's principle. C, Bernoulli's principle works only for laminar flow, and this stream is not. D, none of the above. Well, it turns out that it can knock you down. It's consistent with Bernoulli's principle, but it almost has nothing to do with Bernoulli's principle. And I didn't make this question up. I'm just passing it on. I tried to modify it a little bit to make it a little clearer. There's a difference between the internal pressure. This is the individual molecules moving around in the flow, and the overall macroscopic flow of the whole body of water coming out of that tube with massive momentum. And it absolutely can knock somebody down. I think we all know that fire hoses can knock people down, and they've been used for that historically in very bad ways. So it's not the internal pressure of the water that knocks people down. It's that external momentum of the momentum of the macroscopic flow of the whole body of water coming out of the tube. So don't confuse those two. Your textbook and the textbook provided slides give a number of examples of Bernoulli, and I've talked with experts in this field, and it turns out most of these examples aren't truly examples of Bernoulli's principle. They're combinations sometimes of a little bit of Bernoulli's, sometimes of a principle that we don't even talk about in this class called Coanda's principle, and then a third thing, which is a use of Newton's third law of action and reaction. So I'm not going to quiz you on any of these examples, because what you find is these aren't exactly examples of Bernoulli's principle. And don't blame the author for this, because this is an extraordinarily common misconception. It turns out that if you look online at different articles about Bernoulli that give examples of Bernoulli, or YouTube videos or other videos on Bernoulli's principle that give examples, the examples are 80 to 90% or more are incorrect examples of Bernoulli's principle. So Bernoulli's is really limited to flow of liquids through constricting pipes, not liquids that are not fluids like water or gases like air outside of pipes that aren't constricted in volume. Those are other effects, and it becomes much more confusing to explain that at a far higher level than this course provides. So we're not going to count any of these examples, and many of the examples in your textbook are incorrect, and that is just because a lot of people have a misunderstanding about it, and I do not pretend to have a firm understanding, but I don't feel comfortable giving these examples to you knowing that they probably aren't right, and I've consulted an expert who tells me that most of these aren't right. Okay, so this question as well as will be skipped. Let's move to plasma. Plasma is not gas. It's considered a fourth state of matter. So after solids, liquids, gases, as you give solids more energy, they break up and become more fluid. The molecules or atoms that compose the solid can move around, and then we call it a liquid. And when you give it enough energy, they separate completely, and we call that gases. And now the molecules don't have any bonding, any intermolecular bonding between molecules or between atoms. That's a gas. But if you give it enough energy, now you start breaking up the atoms themselves, and they start losing electrons, and now you've got this gas that's not really just gas. It's a collection of ions that form this new state of matter called plasma. So plasma is an electrified ionized gas. The atomic ions that make it up have been stripped of at least one electron, frequently more, and they're just all buzzing around, very active with a lot of energy and a lot of individual charges, as well as the free electrons in there too. And that's what makes up a plasma. But plasma as a whole is neutral, because if you add up all the positives and all the negatives, they will cancel each other out. But it has a lot of charge in it, and as a result, it will conduct electricity very well. It's full of electricity conducting charges. And because these charges are moving, they can carry electric current, and the electric current can actually cause magnetic fields and be affected by magnetic fields. And we'll talk about that when we talk about magnetic fields and electricity. But so they're very active to both magnetism and to electric current. But the total charge is considered neutral of it. All right. So plasma on Earth is really the least abundant of all the states of matter, of those four I mentioned. I will tell you there are many states of matter beyond these four, but they're really exotic forms of matter that are far beyond the scope of this course. But the four main types states of matter that we talk about are solid, liquid, gas, and plasma. So on Earth, there really isn't that much plasma. There's a little bit, and we'll talk about where it is. Some of it's man-made and some of it's natural. But once you start looking to the rest of the universe, you find that the bulk of what we can see in the universe, the visible universe, is made of plasma. And that's because stars, like our sun, as well as all the other stars, are made of plasma. This is actually a picture of the Pleiades cluster. This is an open cluster of about 3,000 stars. That's part of, it's not the whole Taurus constellation. You can actually see the 6 brightest ones with your own eyes. The rest are too dim to see with the naked eye. You'd have to use a telescope. The reason why I'm pointing this out is just kind of a fun reason. This little cluster, it's not a constellation, it's part of the Taurus constellation. It has a name in Japanese. The name of this cluster, the Pleiades cluster, is in Japanese is Subaru. Next time you're seeing somebody driving a Subaru, look on the back of their car, look at the insignia. It's these 6 brightest stars. All right. The Aurora Borealis and the Aurora Australis, that's the southern version. Okay, these are the northern and southern lights. Borealis is named after the god of the north wind, and Australis literally means south. So the word Aurora Borealis literally means northern dawn, like the sunrise, and Aurora Australis means southern dawn. So it's the northern lights and the southern lights. And you've probably heard of these. Some of you may have actually gotten to see these. I have seen these in upper Michigan, and they are spectacular to watch. They don't look like reality. They're just amazing to see with your own eyes. And these are due to glowing plasmas in our upper atmosphere. And so layers of low temperature plasma are circling the Earth, distant from the Earth, in what we call the Van Allen belts. These are areas where, due to our magnetic field of Earth, have moved charges that have come to Earth either from our sun, from what we call the solar wind of charged particles coming to Earth, and they've been captured by our magnetic field into these bands around us. And then some of it's been directed into the north and south poles of the Earth. So you have a lot of these charged particles, and you might get some that come not just from our solar system, but from outside our solar system. We call these cosmic rays. But these particles, these charged particles, have high energy, and they come in and they interact with the atmosphere. And our atmosphere is predominantly made of nitrogen and oxygen. And when these particles, these showers of electrons and other charged particles from the solar wind or from the cosmic rays come in towards the magnetic north and south poles, they crash into these layers of plasma and produce light. And the light can be yellow the light can be green. That's the most common color. But you'll occasionally see blues, pale blues, sometimes purples, sometimes reds, depending on which element, nitrogen or oxygen, is being interacted with what types of energy particles coming in and hitting them. And if you get a chance to go up north and see them, I highly recommend it. It's really quite the sight. It's almost like somebody is waving a giant curtain in front of your face that has green color on the curtain, and it's just waving across the sky. And you literally see it waving about this speed across the sky. It's just remarkable. All right. Plasma in everyday life. Well, we have fluorescent lamps and we have neon signs, and both of these take advantage of plasma, the fourth state of matter. When you turn a lamp on, there's a high voltage that's generated from the electricity in the lamp, and it's between the electrodes, and that causes electrons to flow. That's what electricity is. It's the flowing of charged particles, usually electrons. And these electrons will hit gas that's in those lamps. It might be neon gas for neon lights. It could be other gases like argon, xenon, and it will basically knock away other electrons from these other atoms, ionizing them, and ionized gas is plasma. Well, this plasma provides a conducting path for electricity to flow through, for current to flow through. Remember, the plasma are charged particles. So movement of charged particles is current. That is what we think of as electricity. And this current can activate other molecules, other atoms that are in the lamps, like mercury atoms. And mercury atoms, when they're activated, when they're excited by all this energy, will actually emit ultraviolet radiation, UV light. And this UV light, we can't see UV light, but UV light can interact with something else, something that we put in the lamps called phosphors. And phosphors are, there are a lot of different ionic compounds, salt type compounds that act as phosphor. And what that phosphors, and that what that is these are phosphor means it's a substance that when it's hit with one wavelength of light, it will generate another wavelength of light. So ultraviolet light is something we can't see. It's too energetic to be in our visible light region. But when it hits these phosphors, it generates a new wavelength of light that is less energetic and just right to be in the visible range, and we can see them. And we actually have different chemicals that will produce red light or green light or blue light. And so we typically will use these phosphors in these three colors and generate different colors of light by combining the blue, green, and red light, because these are actually the primary colors, what we call the primary additive colors of light. You can add them together in different ways to make all colors of light. And so in the case of neon, when it's radiated into a plasma, that'll actually make red light directly without the use of these phosphors. Other inert gases can also be used to make other colors, like a pale blue or maybe even a greenish, I believe. So plasma TVs, another common use of plasma. When we say plasma TV, it's because there's actually plasma in the TV screen. So flat screen TVs are composed of usually hundreds of thousands, the bigger screens even over 1 million. So a 40-inch screen or 50-inch screen has typically over 1 million pixels aligned. And each one of those pixels has 3 little cells that have different phosphors in them. One that produces red light, one that produces green light, one that produces blue light when they're excited by other light hitting them, usually ultraviolet. They also have a mixture of neon and xenon gas to produce some of the other light to activate these. And when the pixels are actually sandwiched between electrodes, so there's an enormous amount of circuitry in a plasma TV. Think about, this TV has over 1 million boxes, and each box has 3 phosphor boxes in it, and each of these is connected up with electrodes. It's an enormous piece of technology when you think about it. And when electrodes charge different areas, different pixels, the current will start flowing through, and the gases are converted to plasma that are floating in the neon and xenon gases. They produce ultraviolet light, and the ultraviolet light hits the phosphors, and the phosphors produce either red, green, or blue light in various combinations. And depending on which charges are activated in which pieces of each pixel cell, you will get different combinations of color, and that's what produces the image that you see on a TV. So it's really quite remarkable. And if you were actually able to look at a TV image that was just frozen and you took a really good microscope, you might be able to see it with a magnifying glass. You could actually see that it's made up of all the colors on the screen are actually made up of little boxes of blue, green, and red on the screen. You could actually see that in a computer screen as well, because computer CRT screens use exactly the same set of phosphors. Well, they may not be the same chemicals, but they produce the same red, green, and blue colors. So plasma can also be used to generate power. It turns out that the exhaust from a jet engine is only weakly ionized. So there's some ions, but not as many as you want. But it's really hot. It's a really hot plasma that's being produced from the back of a jet engine. But if you add the material that comes from a typical jet-like engine, if you add potassium and cesium metal salts to it, cesium metal and potassium salts, these are metals that can ionize very easily and become little positive charges. And as a result, the plasma becomes a much better conductor of electricity. So now you've got this really good conductor of electricity being produced in the plasma. And if you direct this into a magnet, magnets can affect the motion of charged particles. And magnets can create electricity by moving the charges, and moving charges can create magnetism by being moved. And we'll talk about that in other units. But these are self-reinforcing. But it turns out if you direct it through a magnetic field in just the right way, you can generate enormous amounts of electrical power. And it turns out that this is a very low pollution form of power. It's called Magneto Hydrodynamic Power, or MHD for short. And it's already operational in a few places around the world. There are research labs doing it in the US, Australia, Italy, China, Russia, the former Yugoslavia in Bosnia-Herzegovina, So it's being worked on in a number of places. I might have forgotten a couple others, but the idea is this type of energy production is enormously efficient compared to fossil fuel production. To give you a comparison, burning coal in a coal plant will the amount of energy that's used versus how much energy is produced. What's produced is about 35 to 40% of the energy that's put into it, and that's what becomes electricity ultimately. So it's a relatively low efficiency form of energy generation. MHD has a theoretical limit of 60%, and people are typically finding between 50 and 60% efficiency. So not quite double what a coal plant would, but at much higher efficiency. So it's a possible source of very readily available energy that is relatively low polluting to the environment for the future. And with this, we'll stop here.